Good morning. Here we are yet again with another lovely session of CENG 4412 Steel and Concrete Design. This is the 18th lecture in the video series, and today we're going to be looking at really the final material that I want to go over for AISC steel column design. And there'll be two major parts of this video. The first one will cover flexural torsional buckling for members with slender elements. And today we're gonna finish up with steel column design, and then the next lecture, lecture 19, we'll be starting our work with concrete column design. Okay, so let's look at where we've been so far. What we've considered so far. So steel column design. Steel column design. Well, there are three things we've considered so far. Well, three sort of major things we've looked at. Well, we've looked at we haven't looked at torsional buckling. That's more for cruciform shapes and that sort of thing. But what we have looked at mainly is elastic buckling, inelastic buckling, elastic buckling and inelastic buckling. This is going to be your flexural buckling, and this is just more your crushing strength. So these are the major failure modes we've considered so far, and those are part of your main AISC steel design column curve. Crushing strength, or more accurately, I should probably say yield strength. This is your yield limit, where the entire section yields. So again, if you remember from last time and from previous lectures, we have some critical stress. Initially, the column will be governed by yielding, and then past a certain point, we go into more of a buckling mode, an elastic buckling mode. Anyway, next, so for all of this, though, we have not considered flexural torsional buckling. We haven't considered flexural torsional buckling, and really where this occurs is with members with slender elements. And we went into a great deal last time discussing what exactly a slender element is, how that relates to a steel column, really discussing how that arises, that sort of thing. Probably went deeper into the theory, or just I would say deep into the theory, yes, looking at sort of the nature of local stresses, the nature of buckling, the nature of stiffened elements, etc. Okay. And how this is handled, flexural torsional buckling, this is found in section E7 of the AISC manual. And really what I want to do today is work through a long form example. I'm actually going to do the calculations live here to determine the capacity of a slender element column. So this is going to be live. This is going to be a little bit dangerous, because sometimes when you're doing problems live, you haven't worked out in advance, you end up with some unpredictable results. But we'll see what happens. So time to take chances, make mistakes, and get messy, if I can borrow the catchphrase of an old wise instructor. Okay, so I have a design example that I want to work through. And you'll hear me, as I work through this, you'll hear me clickety-clacking on my calculator. Good old TI-89, but anyway. So we have a design example, and it's going to be a fairly straightforward design example, and I want to work through the whole thing, and also this will be a good review of how to work through just the equations of steel column design. Although it will be special because I've particularly chosen a section that will be slender for compression. So I think for this type of thing, this is definitely best illustrated by example. So consider an example here. I have a column. The column has an N on it. It's a column. Let's make sure it's recording here, and we're good. So let's keep going. I have a column. It's going to be made of steel, obviously, but it's going to be made of A992 steel. So this means the yield strength is going to be 50 KSI, and the column is laid out as follows. The upper support is going to be a pin support, and the bottom support is going to be a fixed support. And the bottom support is going to be fixed. And I am given this, or we're given this, and we're also given the length of this thing. And this thing is going to be, say, 13 feet long. Let's just go for the maximum amount of unluckiness by making this thing 13 feet long. And I've particularly chosen this, so this is going to be an interesting example because I've particularly chosen the section and the length to be the sort of the maximum level of annoyance, or at least towards the more complex end of the steel column W section design. And what this section is going to be, let's see, where did that go? That was, I believe, a W14 by 43. Let me double check this really quick in my notes here. Here, if I can get my right section here. I believe, let me double check this. And I know it had a, well, it had a R of 1.92. Yes, so I'm going to let this thing have a, yes, we're going to use a W14 by 53. So this is a W14 by 53, and that'll allow a nice, annoying level of complexity. So we're given this, so we now know basically the entire geometry, we know the materials, and so all of this is given, and we wish to find the phi PN of this column. So I have this section, and I then wish to know the overall capacity of it. So we know the section of it, we know the section, we know the materials, we know the length. I just want to know what is the safe axial load, for a safe factored axial load, that I can apply to this column. Okay, so we're going to start, solution. We're going to start in section B 4.1. We need to determine whether this is a slender column or not. Although, first of all, I'm going to go to step 1, determine if column is slender. Or I should actually say, determine if column has slender elements. And I'm going to first get the limiting ratios, the compact section criteria. So compact section criteria, I'm getting these on page 1-27, just the steel main, just the basically the W-shaped properties. And I see these pre-calculated as here, well, actually not 127, sorry, 1-25. I can see that for a W14 by 53, H over TW is going to equal 6.11, and no, sorry, on H over TW, the B over 2TF is going to equal 6.11, is going to equal 6.11, and the H over TW is going to equal, this is gonna, I need to make a slight adjustment here. I didn't mean this to be a 14 by 53, I meant this to be a 14 by 43, sorry about that. 14 by 43. I need to make sure this has a slender section. Okay, so H over TW, B over 2TF is going to equal 7.54, and H over TW is going to equal 37.4. 37.4. And then I need the limiting ratios that will determine this. So again, B over 2TF is going to equal 7.54, and H over TW is going to equal 37.4. Okay, so, and based on that, we should ideally end up with a slender section. but we first need to prove that. We first need to check if it passes the compact section criteria. So I have basically, if I didn't know this was chosen for this, if I didn't know this was a design example particularly chosen to have a slender section, I would first get these, and I would then go to my table B4.1a and look at the limiting ratios. So this is going to be the allowable ratio. This is again this is the ratio present for the flange, and this is for the web. Then if I go to table B4.1a, I can see that basically for the flange, to be slender or to be non-slender, B over 2TF must be less than or equal to, for the flange, 0.56 divided by the square root of E over Fy. And for the web, H over TW must be less than or equal to 1.49 times the square root of E over Fy. So here, 0.56, we already have the ratio here, but 0.56 times 29,000 over 50. This here comes to, let's say, that comes to about 13.49. So 7.54 is indeed less than 13.49. 7.54 is indeed less than or equal to 13.49. So therefore, the flange is non-slender. The flange is non-slender, but then here, when I do the 1.49, or sorry, yeah, not 14.9, 1.49, times the square root of 29,000 divided by 50, this comes to 35.88. And 37.4 is not less than or equal to this, so therefore the web is slender. Now, let's look at this. In many cases, you would so depending on how you want to design your members. In many cases, flexural torsional buckling is one of these things that's actually, at least for W sections, is actually frankly easily avoided. So in many cases, if I was actually designing this, I would just say, you know what, it's actually most shapes in the AISC manual are going to be non-slender for compression, or at least most W shapes are going to be non-slender for compression. So for certain shapes, like certain built-up members, it's much more difficult to avoid. But for most of your standard rolled shapes, most of them are non-slender for compression. If I was designing a column and was just using off-the-shelf rolled shapes, I would probably just go to the next highest shape and say, you know what, let's just not worry about this. But I do want to go over this because, especially for more built-up shapes, often you're going to you're not going to be able to avoid non-slender elements, simply because if you're building something out of plate, oftentimes it's more difficult to avoid slender elements. I could do this with a built-up section, but the nice thing about using a rolled shape is all of the section properties are already calculated for us. That allows us to move through the design example a bit quicker. Okay, so because of this, we are going to need to use section E7. So we'll need to use section E7. Section E7 for our columns analysis. All right. Now, if we turn to section E7, if you read through this, what you will find is that really this is based off of a philosophy of reduced section. So E7 is based off of reduced section. The big idea: reduce the cross-sectional area. Reduce the cross-sectional area. So, for example, or effectively, okay, basically what we're trying to do is we will calculate for the big idea basically, for a slender web or flange, that is subject to flexural torsional buckling we will calculate an effective area for a member that is not. We will reduce the cross-section, the allowable cross-section, basically. So for example, let's say we have a W section that's something like this. But we find that this thing has a slender web. Here. Let's see. And we find that this thing is slender. So what we're going to do is we are going to effectively transform this, and this works because column strength is about cross-sectional area rather than, say, moment of inertia. What we're going to do is we're just basically going to reduce this into a column that has maybe a squatter, less slender web. We're not actually going to redesign the member. Basically, we're going to say that basically this was the original area, and this is our effective area. We have shrunk it down. We have collapsed it and said, okay, well, we know that this element here, this section here, has a slender web. So we're going to reduce the height of this thing. We're going to reduce the height of the member, or reduce the height of the web, or reduce the height of the web to the point that, okay, well, this section is effectively equal to this section in the sense that, and then once we have that, we can just calculate its strength based on normal column strength design. But I think this is maybe best shown by example. So, if we look in section E, section E7. In section E7, this is split up into two subsections, one for slender element members excluding round HSS hollow square tubing, and one for hollow square tubing. The equations are just effectively different. For our case, we're going to be in section 1. And we see that P nominal, the nominal strength, is going to be FCR times area effective. FCR is going to be computed the same way that we've looked at already, computed the same way for previous analyses as before, but the area effective is our reduced effective area. So the first step here is actually going to be to calculate the FCR from the previous case, or from the previous sections that we've already looked at. So I want to do that, and this will also serve as a useful example for calculating column strength for non-slender elements. So here, I want to calculate this. Let's see. Oh, and I'm going to go back and mention here that this is referred to, if we go back to the table, we'll see that this is referred to as lambda r, our non-compact, our non-slender ratios. So here, this 13.49 is going to be our lambda r, and this is going to be our lambda r here, and this is going to be our lambda, and this is going to be our lambda. But we'll come back to this later. So here, the first thing we need to do is we first need to calculate, let's first focus on calculating the critical stress, FCR, according to the previous sections. And for our member here, for our wide flange, this is going to be based on section E3. We know that this actually says without slender elements, so at first it may seem weird to use the equations from section E3 because we know this is actually a slender element, but that's okay. We're going to then reduce the effective area to take into account the slender element effects. So here we need to calculate FCR, And if we go back to section if we go back to section E3, we can see that we need to first look at whether we are looking at whether we're looking at elastic or inelastic buckling. So the first thing we need to do is to calculate whether we're in the case where LC over R is less than or equal to 4.71 times the square root of E over Fy. And we know that LC is basically KL, so we're really asking is whether KL over R is less than or equal to 4.71 E over Fy. So K, now if we go to section 16.1-570, our layout of columns, our effective length factors for columns, we can find that the type of column we have here, if we go back to this, the type of column we have is a fixed pin column. So for our case here, K, if we go to this table for the fixed pin case, K is going to be equal to 0.8, and the length is 13, or 13 times 12 to convert to inches. And then we need R, and we're always going to use the R that is least. And if I go back to my section properties, I guess that's on page 1-25, for our 14 by 43, I can see that RY here is 1.89 inches. So this is inches, and this is inches. 13 times 12 inches, and then RY is going to be 1.89 inches. I need to see whether this is less than or equal to 4.71 times the square root of 29,000 divided by 50, our yield strength, or our yield stress. And so then this collapses to, if I run through the calculations, I'm just going to throw this in my calculator. My KL over R is going to be 0.8 times 13 times 12 divided by 1.89, and this comes to 66.03. 66.03. And I'm seeing whether this is less than or equal to 4.71 times the square root of 29,000 over 50. And that is then the square root of 4.71 times the square root of 29,000 over 50 is 113.4. And we find that this is indeed true. So we're actually going to be in the inelastic, or sorry, I guess this would be the elastic buckling region. So we're going to go back to chapter E and know that we are, and see which equation we're going to be using. And we can see because of this that we are going to be using equation E 3-2. Okay, so we need to calculate, our next thing to calculate is going to be our FE, not our FCR, but our FE. FE is going to be pi squared E. This is equation E 3-4. So FE according to E 3-4, and FE is going to be equal to pi squared E divided by LC over R, quantity squared. LC over R, quantity squared, and thankfully we've already calculated this. This is our 66.03. This is basically LC over R, and we can reference that going forward. So 13 times 0.8 times 13 times 12 over 1.89. So basically then I can just go pi squared times 29,000 divided by our 66.03 quantity squared. Pi squared times 29,000 divided by this squared, and that comes to 65.64 KSI, so over the yield strength. So we're going to be in the elastic buckling region. Here, So now I can feed this into equation E3-2. So FCR then is going to equal, so now I apply FCR via equation E3-2, and FCR is equal to the quantity 0.658 times Fy over Fe. Here, times Fy. So that's going to be 0.658 times 50 divided by 65.64. This quantity times 50 here. And then I can simply go and say, okay, here, 0.65, I'm just going to put this into my calculator, to the 50 over 65.64 power times 50, and I get an FCR equal to 36.35 KSI. So FCR is equal to 36.35 KSI. 36.35 KSI. And this value, we're going to take this and feed this into section E7. So we're going to go back there now. So yeah, so when dealing with slender elements, we do just kind of dance around chapter E. But let's keep at it. So the whole idea here is that for section E, we need to calculate a reduced cross-sectional area. So now here, for E7, Pn is going to be FCR times area effective. In the previous chapter, in a previous section, in section E3, you don't use this, so let me just do this as a little contrast. In section E3, you're not using area effective, you're using area gross, the gross cross-sectional area. In E7, you're using a Pn equal to FCR times area effective. And again, this is a reduced allowable cross-sectional area in order to take into account the effects of flexural torsional buckling. The reduced cross-sectional area. And so looking here then, we can say, let's see. So if we look at this, this basically gives us instructions on how to reduce the effective width of slender elements. So for our cross section here, for our W section, there are two elements, the web and the flange. So let's look at the original cross-sectional area before. And later I'm going to compare this to the reduced cross-sectional area. So I'm going to draw out our elements. And I want to get its properties. Oh, lovely. I'm going to go back to section 1, chapter 1, and get its sort of its full properties. So let's see here, back to page 1-25, and we'll need this in order to reduce its area. Here, so we know that this thing's depth is going to be 14 by 43, the W 14 by 43. Its depth here is that is going to be 13.7 inches. 14.7 inches. And we also know here that it's let's say its depth is 14.7 inches, and the thickness of the web is here 0.305 inches. We know that the thickness of the flange here is 0.53 inches, 0.530 inches, and we know the width of the flange here is going to be 8 inches. And let me just do a quick calculation here to confirm something. Let's see. So let's say minus 2 times that. 14 by 43. Yes. Let's see here. I want to confirm something here. Divided by 0.305. Yes, and so we're then at 13.7 minus 0.53 times 2, and that divided by 0.35. This is bottom right. Okay. I need to confirm something really quick here. So this. This is. Okay. I'm just trying to confirm my H over TW calculation. Yes. Okay. No, that makes sense, I guess. Here. Divided by thickness of the web. That's closer. Okay. I guess that includes all the fillets and everything else, so yeah, that's fine. Okay. So we do have to be careful with our H over TW calculation because that's going to include the distance from the fillets and the full unreinforced distance. So anyway. Because if I do a H over TW calculation just using depth minus 2 times the thickness of the flange, I get slightly different values than the 37.4 I quoted earlier. So we do have to be a bit careful with that. 12.64 divided by 0.305. Yeah, we get a slightly different value, so we do have to be a little bit careful with that. Here. Okay, anyway. Back to this though, so I'm just going to use the H over, okay, the whole idea of this is that we're going to reduce the allowable height of this thing. So here, but I'm just going to go ahead and use the gross cross-sectional properties for this, just to give you an idea. But here, going to section E, E7. Basically, what we're going to do is we are going to see for each element, first we need to check for each element whether it's slender or non-slender. We already have that though, so we know our flange is is non-slender, so we can just use its gross area. This is non-slender, this will not be modified. The web is slender, so we're going to have to reduce its h. So we first need to figure out which case we're in. We need to figure out whether we're in case A or we're in case B here. So we need to check whether lambda is less than or equal to the square root, actually lambda r, times the square root of fy over fcr. And previously, we calculated that for our web. So again, so if you look here, again in section E7, it says for slender element members, the effective width for only slender elements will be calculated according to the final equations. So for our non-slender elements, like our web here, or sorry, for like our flange here, we don't need to do this reduced area calculation. We only need to do the reduced area for the web because only it is slender. So here then, our lambda that we got previously, our lambda, if we go back here, for our web, our lambda is going to equal 37.4. And this is less than or equal to lambda r, which we got previously was 35.88. $35.88 here. That is the 1.49 times square root of 29,000 over 50. Okay, but then this times the square root of 50 over FCR, and FCR is the 36.35. Now you do, like I mentioned, actually I'll finish this and I'll give a bit note on the lambdas. So here, first let's get this. The 35.88 if I can go up and grab that. Where did that go? Okay, 35.88 times the square root of 50 divided by 35.65. And this is 37.4 is less than or equal to 42.49. And actually, what do you know? We're fine. B effective is just equal to B. Okay. So we find that we actually don't need to reduce its area. I guess it's fine by the slender element criteria. That's a bit odd, but that can happen when you're doing problems live sometimes. Otherwise, what we would do is, let's see, let's double check this. So lambda r, again, I want to double check this because we did calculate that this was, because I do know that this is a slender element. So that does bother me a bit, but I suppose I suppose this FCR also depends on the length of the member, so it's actually not surprising that we could end up with something where we're not actually experiencing lateral torsional buckling, we don't actually need to reduce its effective width. But anyway, let me just explain what this would work, how we would work with this, even if we did have to reduce it. So, or actually, let me just go ahead and finish this problem out. So we see that B effective is actually equal to B, so we don't actually need to reduce, do not actually, for this particular problem, do not need to reduce the height of the flange, or sorry, the height of the web. So, and if you look in the notation here, it says for webs, H effective is your B effective. You're just substitute, instead of using B, you're using H. So really, this equation is basically saying here, H effective is just equal to the H of the member. So we're not actually, for this particular problem, because of our length, because we are, our element, even though our element does have a slender element, even though our member has a slender element, the effective area of the effective height of our web will remain unchanged. Of our web will remain unchanged. So, however, if this was not true, and really this is because this equation A and B here basically sees what region of the buckling curve you're in. For our column, it's relative. We found that we are not going to be in the range where it's important, but if it was, we would have to use equation E7-3. So if this check did not pass, we would reduce the area of the height of the web. We would reduce the effective height of the web by equation E7-3. So the effective height, H effective would be H, and I'm modifying this, replacing B with H. H times 1 minus C1 divided by the square root of FEL divided by FCR times the square root of FEL over FCR. And the manual goes on to give definitions for all these things. C1 is just a constant found in table E7.1, and FEL is the stress laid out in equation E7-5. It's just another reduced stress that you need to calculate. So for this particular problem here, we don't need to worry about this. For our problem here, or our column here, because the H effective is just equal to H, the area effective for our column here is just going to be equal to the gross area. So if our column was longer, we would have probably had a more critical case, but here we passed our FCR was low enough that this didn't apply. Or actually, our FCR is high enough that this didn't apply if you look at the mathematics, but anyway. So here then, we just run through the equations. Phi PN, or PN here, is just going to be equal to the gross cross-sectional area, or FCR, times area effective, which for us is going to be equal to FCR times the area effective, which is our previous 36.35 KSI. And we want to get the gross cross-sectional area. Again, found on page 1-25. We're just going to keep going back to there. So the gross cross-sectional area is 12.6 inches squared. And this is, so 36.35. Or let's see, was that, yes. Actually, let me go back to here. FCR, where did I calculate that? Yes, 36.35, let's grab that. Times our gross cross-sectional area of 12.6. And PN, the nominal compressive strength, nominal axial strength, is 458.0 kips. And therefore, design strength, phi PN, is our phi, which is going to be 0.9. 0.9 times 458.0, or simply times 458. Oh, no, this times 0.9. And I get 412.2 kips. And that would be our final design strength if I manage to not screw this up, which is a certain possibility when doing a problem live. Okay, so that's the basic idea. Now, I do wish I should have recalibrated this I should have probably chosen the length a little bit better, so I was hoping to end up in that second region, and I would have to play with this a bit more to make sure we got a column length that was in that region. Maybe I'll try to put together something later that does have that. But anyway, I hope this does give you the idea for how this section E7 works. Basically, if we had found that we were in that second region for E7-3, we would have reduced the effective height of our web, basically. We'd have basically shrunk it down and said, okay, what is the new cross-sectional area of this collapsed column? And based on that reduced cross-sectional area, we would have used that as our area effective. And that's the basic method for calculating flexural torsional buckling, and that will do it for this part of the lecture. And as always, thank you.